In this lesson, we are going to implement a binary heap. So in the previous lesson, we had seen that a binary heap can be either a min heap or a max heap. So in the min heap, all the elements of the complete binary tree are more than the root. And that's true for all the nodes and all the corresponding subtrees. So that is min heap. Similarly, max heap is the opposite. So in this lesson, we will implement a min heap. The implementation of max heap would be very similar. So if you remember from the last lesson, the root is the minimum in the min heap. That is, if h is the array, underlying array, then the minimum lies at the root, that is first position or index 0 in the array. And typically we implement this binary heap as an array. So underlying container is an array or a vector. Similarly, if you look at the parent, if you want to find the parent of ith node, then that will be I minus 1 by 2 integer division. So parent for 2 is 2 minus 1 by 2, that is 0. Similarly, parent for 1 is 1 minus 1 by 2, that is also 0. So parent for these two is 5. So we are talking in terms of index. So for indices 1 and 2, we can find the parent like this way. Similarly, left will be 2i plus 1 for the node I. So this is node I. Its left will be 2i plus 1 index. So whatever is the container, you can get that value. Right will be 2i plus 2. So now let's implement a min heap. So in min heap, the requirement is that you should be able to get the minimum element that you are working with. You will be working with a number of elements. In many problems, you are, for example, you are getting a stream of numbers and you want to keep track of the minimum, and you want to be able to get the minimum in constant time. So there we use a binary heap or min heap. So the requirement is that this get min operation should be O of 1. And you can see that it's really O of 1 because you can directly go and access the container at index 0. So that is O of 1. Then you should be able to add a new element to this heap. So we need another function for inserting a value, getting the minimum. We should also be able to delete the minimum. So we will come back to time complexity of all of these later. And then you can additionally want to query how many elements you have. So you may want to have a size. So these are the public methods that we will expose. There are some other private methods which we will not expose. So these will be private methods. And then we should have a container. So this heap will be an array or a vector. So again, these are all constant time. These three, we have to directly access. We directly know the index of parent, index of left, index of right. So we can directly access them in constant time. So clearly these are O of 1. EP5 is an operation which we need to discuss. So EP5 means that, and you see that there is an index to it. So these are all different functions that we will implement. Now let's see EP5. EP5 I, index I. So let's say we want to heapify at some index. Let's say we have a heap, a min heap. So we have 5, then we have 7, 12, and then we have 20, 25, and here we have 13. So this is a min heap. All the nodes are valid. But now let's say instead of 7 here we have 57. And we have, let's say, a few more nodes, 15, and here we have 30. So you see that this part is valid. So this is a min heap. This part is a min heap. The entire left subtree. This is a min heap. This also is a min heap. But at this point 57, this min heap property is violated. Why? Because this 57 should be less than all its children, which is not the case. So here we will call EP5, and this is index 0, 1, 2, 3, 4, 5, 6, 7. So we will call EP5 of 1, because at this index the min heap property is violated. So what this EP5 will do, it assumes that this EP5 operation assumes that the heap property is violated only at this index. In all the other subtrees, in the other parts of this tree, the heap property is satisfied. So, and above this also heap property is satisfied. So this is the first index where this is violated. Above that there may be many parents and everything is fine. So we are only concerned about this part of the subtree. So we will see, we will compare the two children of this node. Since this is a binary tree, it will have two children, complete binary tree. So we will see that minimum of these two is 20. So we will pick 20 and replace it with, we will swap their positions. So now it has 20 and here we have 57. Now it's valid. Now this part is the only concerned part. So we have reduced the level of the height of unbalanced heap, or the subtree violating the heap property by 1. So its height was from here. So one level we have reduced. Why this will be valid now? Because this 20 was less than 25. So all the elements below 25 would be more than 25. So now the parent of 25 is 20, which is less than 25 and less than all of its children. So this will satisfy the heap property in all of this part. So now we have 57 here, 25 was here, and maybe some more subtrees here, and here we have 20. So now we are concerned only in this part. So here we have just one children, or if we have more, like let's say 27, then minimum of these two is 27. So we swap this with 27 and 57 comes here, and this will continue along one of the branches. So it may take some value like this, and this largest value, let's say this value was larger than its both children, and maybe after reaching here, so it will propagate downward along one of the paths, not both. And maybe this is A comes here after some time, and this is already less than both of its children. Then we will stop here, but in the worst case we may have to go till leaf node. So worst possibility is it will take O of H, or number of, or the height of this subtree starting from this level, or in the worst case the complete height of this complete binary tree, that is O of log n. N is the number of nodes. So this is the purpose of EP5, and it can take log n time. So the time complexity for this can be log of n in worst case. Now for delete min, we have to delete this root node. This is the minimum, and after that what we will do, we will, whatever is the last element, we put it here. So let's say we want to call delete min, then we will remove 5. 5 is gone. So we put 12 here instead of 5, and this 12 is gone. Delete it from the end, put it here, and remove the root node. So this was constant time, just putting 12 here and deleting 12. Now we will call EP5 at index 0. because we have put some value larger than some of the nodes at the root. So the heap property is not satisfied at the root. So we will call EP5 0. So EP5 takes log n time. So this delete min will also take log n time. And size is a constant operation. We just keep track of the count. In fact, we can directly call the size of the underlying container. So now you understand all the functions. So let's implement all of these in C++. So first we need to define a class. So we will define a class called minHeap. And it will have a container. We can keep a vector. You can also keep an array, but many operations will be easier since these are already implemented in vector. And let's name it heap. And let's define some of the private APIs which we will not expose. Parent of I. So left index of left child is 2 times I plus 1, and the index of right child is 2 times I plus 2. And then we will need the heapify thing at some index I. And since we are using vector here, we will need to include vector. So in heapify, we need to compare the current value with both of its children and then take the smallest. So left index is left of I, right index is right of I, and we have to take the smallest. So let's initialize the smallest with I. Maybe that this I is already at the lowest level. It's one of the leaves. So for this, left and right will be null. So we need to add some check that these left and right indices are valid. So if L is less than heap dot size, then this is a valid, this is non-leaf index I, and this L value of element at this index L is less than the current index value, then smallest is equal to L, else smallest will remain the index I. And the same thing if R, this is valid, and heap R is less than heap smallest, then we got even a smaller value. And if smallest is this index I itself, that is this current index was itself the smallest, then no need to heapify. It's already a valid heap property is satisfied, so no need to heapify. But if smallest is not equal to I, then we need to heapify further. So we will call swap. You can define your own swap also. You can even ignore this std since it's already we have written it here. So we swap the current element with the smallest. And heapify continues below that. So now these private APIs are written. We will implement the public APIs, which will be get mean, then we will have so let's define get mean. It's very simple. We have to simply return heap 0. You can also add a check here, so let's add it. So if heap is already empty, then return some value, some default value which will not be part of the heap. Let's call -1. Let's say the heap only contains positive values. Otherwise return heap 0 or heap dot front, both are same things. So get mean is defined. One of our APIs is ready. Next we will add the API to insert an element. So insert int some key k. So how do we insert? So when we have to insert, we will just put it in the end. So let's say we want to insert 3. Let's say this is the original heap and we want to insert 3. So what we will do, we will put it in the end. And then, so by inserting this, heap property can be violated only along this branch, because it was a heap earlier before insertion and we are not changing any other thing. But this may be smaller than its parent, and above this everything is valid. So we may have to again check upwards along this path. Its parent is its parent until we reach the root. Maybe this is even smaller than root. So we check with its parent. If it's lesser, then we swap it with parent. In this case 3 is less than 8. So 3 comes here, 8 comes here. Now again we compare it with its parent. Again 3 comes here, 5 comes here. Now this is a valid heap. Why it will not violate the heap property of any other branch, left subtree? Because earlier here was 5 and we have which was less than all of its children. So less than all of its children in left subtree. Now we have moved as even a smaller value. So that will also be less than all its children. So heap property will not be violated anywhere else due to this insertion. So again in the worst case we may have to go all the way up. So that will take login time. But it can stop before that also. Let's say instead of 3 it was so let's say it was 7. So we simply add 7 here, compare it with its parent. It's less, so we put 7 here and 8 here. So we are swapping. Now we compare 7 with its parent. It's larger, so we stop. No need to swap anything. It's valid. So worst case is login. So now let's implement this insert. So pushback will push the element to the end. And after that we have to keep looking in its parent until we find a parent which is smaller than this value. So the last index is heap.size -1. So until we reach the top, and parent of I is more than this value, we continue. Heap I with its parent. And then we update the I. So either its parent is less or we reach the top node, the root node, then we stop. So that's it. We have inserted an element. Now next we will define the delete min. Delete min. So remember, the minimum is the root, so we have to delete root, but instead of deleting root, we will put the last element to the root, delete the last element, and then heapify from root. So let's add a check that if heap is empty, then we don't need to do anything. If heap is not empty, then what we will do, heap 0 is equal to heap dot back, the last element. You can also access it using this index. So now the last element is at index 0, then heap dot pop back, we remove the last element. So now the root is gone, the earlier root, and there we have the last element, and it's gone from the end also. And then we simply called heapify at root. That's it. We have deleted the minimum element. Next, size. This is probably the simplest one. So just return heap.size. So this vector is already keeping track of the size, so you can call the size of that vector. Then let's define a function to print the heap. So this will be useful for our own purpose for debugging. Now we have implemented all of our methods, and we will create a heap, min heap, and add some elements to it. So let's insert the same set of elements which we had seen in the example. The order may be disturbed slightly. So we have 20, 8, 12, 15, 10 and 5. So let's insert them in random order. And now let's print the heap. So it will print in level wise order. So first the root, then the next two nodes, then the next 4 nodes, and so on. And let's run it. So it prints 5, 10, 8, 20, 15, 12. So let's draw the tree. 5, 10, 8, 20. 5, 10, 8, 20, 15, 12. 15, 12. So this is slightly different from our original tree because we have inserted in some order, but you will see that heap property is satisfied. 5 is the root, which is less than all the nodes. Then 10 is less than its 2 children. Then 20, 15, 8 is less than 12. So it's valid tree. So it's working. Now let's delete some value or get the minimum. Then what we will do, we will delete min, and then we will print the heap again. So it deleted 5, which was minimum, and now the heap is 8, 10, 12, 20, 15. 8, 10, 12, 20, 15. So 20 comes here, 15 comes here. So again it's a valid heap. So what it would have done, so we removed 5, so it put 12 here and 12 is gone. So it checks which child is minimum. 8 was minimum, so 8 comes here, 12 comes here, and now you see these two are same. 8, 10, 12, 20, 15. So that's why it prints in this order: 8, 10, 12, 20, 15. So I hope you understood how this min heap was implemented. If you understand this, you can simply implement max heap. So I leave it as an exercise to implement max heap, and that should give you a good practice. So see you in the next lesson.